All right. So signal manipulation stuff is what I want to talk about first. So basically what this means is shifting and reversing and scaling of signals. So time wise, particularly, if I say time shifting, like if I have a signal, all right, let's say the unit step that looks like this. And I said I want to plot u of t minus 1. So this is u of t. How do I plot u of t minus 1? Let's call this guy, I don't know, I'll call that f of t. How do I plot that? I shift it and I shift it which way? To the right. Now, the way I can think of that, so I'll skip over to here for a second. So here, um, that's the original signal here. And then I want to plot a function that is basically the same function, but shifted to the right. All right. So when I deal with that kind of thing, how do you know it's shifted to the right? Just because you remember that a minus means to the right and a plus means to the left? How can I check? Well, let's look at f of t and g of t. So g of t is this f of t minus 1, right? So let's do this at different values of t, okay? So at t equals minus 1, what's this guy equal to? 0? Yeah, 0, okay? G of t is equal to f of t minus 1. So here I'm evaluating what? F of minus 2, aren't it? So that would be equal to 0. So how did I say it was f of minus 2? Did I come up with that? Yeah, plugged in t equals minus 1, right? So minus 1 is minus 2. Okay. All right. So now if I plug in t equal to 0, it's a little odd, but f of t is, we say it's kind of undefined there. I'm just going to say it's 1 because that's where it jumps up. All right, I'm playing a little bit of a game, but I'm going to call it 1. This is f of what? F of minus 1, which is what? 0. Okay. So now I plug in t equal to 1. At t equal to 1, f of t is clearly equal to what? 1. What's g of 1? Well, that would be f of what? 0, which is where it goes equal to 1. So that means that right here at t equal to 1 is where this guy jumps up. And let's just be clear, this is 1 and this is 1, like that. All right, so the reason why I know it shifts to the right is why? Well, because of what I just proved, right? That's why I know it shifts to the right. Now, one thing to bear in mind, there's a term that we often use for this because we're talking signals, right? We're talking voltages and currents. We're talking about things that happen in the real world. So that the x-axis is usually time, right? But because it's time, like I'm thinking of like I'm measuring a signal that's moving forward, it's a little bit hard to think about this. You just look at a graph like this. But if I were sitting in real time, if I'm at time t equal to 0, when is time t equal to 1 second? Right now, with t equal to 0, t equal to 1 second is in the future, isn't it? Right? So that means that what would I call this? I would call this a delay, right? Because I'm making something happen in the future. I'm delaying it from happening. So when I move to the right, it's a delay by 1. If I move it to the left, it's going to be an advance, right? Because if I make something happen at t equal to minus 1 that was happening at t equal to 0, that's an advance. I made it happen earlier in the timeline of the world. Okay. So if I have, so basically our general idea, so the thing that you guys know pretty well is that shift left and right. You learned that pretty well probably in algebra in high school. All right. So if I have an original signal f of t, in general, I talk about having something where I have f of at plus a shift of some kind. And we want to talk about how to deal with that. So if t naught is greater than 0, so the basic way I did this, right? Which direction do I go if this guy is positive? Which direction do I shift the signal? This would be, so shift left, which we called what? An advance or a delay? in advance. Yep. Because I'm making it happen earlier in time, right? Seems like an advance when you think about if something happens at t equal to 1, at some level that might feel like an advance if it was happening at t equal to 0, but that's the later in the timeline of the world, right? That's why we use that terminology. All right. For this guy, it would be a shift right, the opposite. This we called a delay. Okay. Now, we're going to get to this in a second, but A applies a scaling on the time axis. All right. I want to get back to this one because I feel like, again, if you try to use your intuition, initial intuition, this is probably going to do the opposite of what you think it's going to do. All right. So let's come back to that one. All right. So we did this example already, right? If T naught's greater than 0, we shift to the left. T naught's less than 0, we shift to the right. You guys understand this one fairly well. The harder one is when we get to something like, say I've got this guy here, right? So I've got this goofy looking function. Here's t equal to 0. This function, I say it's goofy. The function is sine cubed 2 pi 100 sine cubed of 2 pi 100 t. All right. So that underlying sine function, what's the frequency in hertz? What is it? 100 hertz. All right. If I see sine 2 pi 100, you should know that that's 100 hertz. Okay. If there's nothing that you remember after the class is over, hopefully that's one of the things that you remember. How to get to the period, the omega, and the f. Okay. That's important. All right. I'm fully well aware of the fact that shifting and scaling of signals 10 years from now, you're probably not going to remember. Frequencies, periods, remember that. Okay, that stuff is important. All right. Okay, so when I look at this guy, let's say I want to compute f of t minus 0.003. So what does this do if I have a minus 0.003? What's that? So if I have a negative number here, what's a negative always do? Which direction do I shift? I shift to the right, which is a delay. Yeah. So it's a delay. But how do I plug that in to figure out? So g of t. Okay. How do I plug that into f? So f was sine cubed 2 pi 100 t. So how do I plug that in here? Because I have like a factor here kind of multiplying the t. So I'd say what? I'd say sine cubed of what? How should I write that? Yeah, so this is basically what I'm saying is this t minus 0.003 plugs in for the argument t. So it becomes 2 pi 100 t, right? 2 pi 100 times t minus 0.003, like that. I plug in the t minus 0.003 for where the t was, all right? And you learn that when you learn kind of basic functions and math 2 or whatever they call it these days, right? When you learned that stuff there, you kind of learned that. All right. And so what this is, like I said there, this would be a 3 millisecond delay of the signal. All right. So if I look here, this is my f of t, the original one. So it's shifted over to that guy. Now, what happens if I did the other way? If I did let's say I did g of t equals f of t plus 0.003. Which direction would I go? I go left, right? So basically here, right? I moved it to the left. And we called that in advance because that signal, everything that was happening in that signal is now happening earlier in time. All right. So again, the key thing is here is when you determine this function g of t, you replace the whole time argument. In other words, you replace the t with the t plus 0.003. All right. So you wouldn't, the key thing is some people might look at that and say, well, if it's sine cubed 2 pi 100 t, they might just do this, right? That's not correct. All right. You do not do that. What you do is you're replacing the entire argument like I've written out right there. All right. That's always kind of the key thing. Right? Again, simple concept, not too difficult. You've seen it before, but the notion of calling it advances or delays is kind of a new thing, probably because this is the concept or the language that we use when we talk about signals. All right. So, what if I said f of minus t? Well, you replace the time argument with a negative t. What does that do? It says, well, mirrors it across the y-axis. I wrote it there. What's that going to do? What's that? Yeah, flip it across the y-axis. So where I've got a peak here, that peak should be happening over there, right? A time reversal. I'm making everything in the future happen in the past, right? Is basically what it means. Okay. All right. In general, what I say if I have a scaling, right? So in this case, if I have a function f and I scale the time axis somehow, the function g here, basically, it gets scaled one way or the other. If a is greater than 1, the signal gets compacted. If that scaling factor is less than 1, it gets expanded. And the key thing is here, what I'm really talking about is, I should say a is a number greater than 0, right? Because if I apply a negative, then I get this scaling. But if I think about just the magnitude of a, maybe I should think of it that way. If I just think about a positive number a, okay, I'm thinking about the positive number. If I have a negative, then I deal with that reversing. But if that positive number I have, if it's greater than 1, the signal gets compacted. If it's less than 1, it gets expanded. All right, so let's figure that out. Okay. So here I have this function f of t, which this guy gets a name oftentimes too. This guy is equal to 1 from -1 to 1. This function, any idea what this would be? It's a function that's 0 everywhere, except he comes alive for 2 seconds and is equal to 1, and then he dies again, right? What do we call this? It's pretty common in digital. I'd say this is a pulse, right? Right. So you can make a microcontroller make a pulse for you for 2 seconds, right? This would be a microcontroller making a pulse, right? Very common signal to make. All right. So f of t is that guy right there. So what I want to plot is g of t, which is f of 3t. Okay. And so I basically went along from t equal to 2 to t equal to -1 to draw this guy. All right. So g of 2, what's that equal to f of? F of what? F of, okay, so at t equal to 2, all right, t equal to 2, I say f of 3 times 2, so f of 6, okay? What's f of 6? So this is f of t right here, just to be clear. All right, so this is 1 here. So f of 6 is off the screen. It's equal to 0, right? All right. So t equal to 1. G of 1 is f of 3, right? Because it's 3 times 1. What's f of 3? Well, here's 2, 3. Here's f of 3. Okay, f of 3 is equal to what? 0. All right. Now I do t equal to 1/3. All right. So at t equal to 1/3, I have g of 1/3 is f of 3 times 1/3. What's 3 times 1/3? 1. So what's f of 1? 1. Okay. So g of 0 is the same as what? If I plug in t equal to 0, what do I get? I get f of 0, that's equal to 1. T equal to -1/3, that's so g of -1/3, I get f of 3 times -1/3. What's that equal to? That's f of -1. F of -1 is what? 1. And then g of -1, what's that? Well, that's f of 3 times -1, so or f of -3. Where's that? Well, that's over here. What's that equal to? 0. So I say I've compacted the signal here, right? Why have I compacted it? What have I done? If I follow those values, it basically tells me that this guy is 0 until I get to -1/3, and he jumps up, and then he comes down at 1/3. and then he stays at 0 for a while, like that. So I compacted. It's basically it's a third, or well, it's 1/3 the size on the y-axis, on the x-axis, right? 1/3 the size on the x-axis, right? So what was it -1 moved to -1/3. What was it 1 moved to 1/3. So it's 1/3 the size. Hasn't changed its value on the y-axis at all, right? But it's compacted in time. Now, what happens if I get this guy? So now I have, this is where I'm saying A is less than 1. So in this case, I've got a scaling factor of 1/3. This is going to expand the signal. So let's try this. So t equal to 4, I say g of 4. That would be f of what value? So if it's, so 1/3 of 4. So f of 4/3. Where's 4/3? 4/3 greater than 1 or less than 1? Greater than 1, right? So that's 4/3 is probably right about there, right? So what's that equal to? 0. All right. T equal to 2. G of 2, I have f of 1/3 times 2. So f of 2/3. Where's 2/3? T equal to 2/3. That'd be right about here, wouldn't it? What's the function value f at that point? 1. Okay. Now t equal to 1, g of 1 would be f of 1/3 times 1. What's that equal to? Well, that would be here. That's equal also to 1. If I keep going with this is going to be f of 0. That'll be 1. What do you think is going to happen at -1 and -2? Well, -1, g of -1 would be f of 1/3 times -1, or f of -1/3. Where's that? Well, that's here. That's equal to 1. This guy would be f of -2/3. That's equal to 1. At t equal to -4, g of -4 is f of 1/3 times -4. So f of -4/3. Where's -4/3? Where's that? That's over here somewhere, right? That's equal to 0. All right. What have I done? So this guy clearly at t equal to, if I follow from -4 over to 4. So if I go up the time axis from -4 to 4. At -4, it was 0. At -2, it was 1. -1, it was 1. 0, it was 1. 1, it was 1. And then by the time I get to t equal to 4, it's back to 0 again. What have I done? I've expanded it, right? Where does it start to go high? I didn't do that value exactly, but you should be able to see the pattern. Where does it go high? So it's going to be low, and it's going to go high, and it's going to go back down. What are the two edges where it goes high and then goes back low again? -3 and 3, right? -3 and 3. So it's expanded by a factor of 3, right? That's a time expansion. Okay. And you can do that kind of stuff digitally, right? You can expand things once you've read a signal into a microcontroller, you can expand it. You can play it back and have it be bigger. All right. Now, question is, what happens if I have a compound combination? Right? So I've got this G of T equals F of AT plus a shift. All right. When I have this, the right thing to do is to apply the scaling first and then apply the shift. All right. Apply the scaling first and then apply the shifts. Now, I did that when I did that example earlier with that sine cubed function. That means that I got to look at this thing as what? F of A times T plus T naught over 2. Okay. Not over 2. What am I doing? T naught over A. Okay. All right. So the first thing I do is apply the scaling. The second thing I do is apply the shift. And the shift that I apply is that T naught over A like that. Okay. So let's check this guy here. Here's my function f of t. And I want to make the function f of 2t plus 2. Okay. So I'm going to write that as what? Factor the 2 out. If I factor the 2 out of this expression, both terms in there, it'd be 2 times what? 2 times t plus 1, right? 2 times t plus 1. So the step that I do first is the scaling. The step that I do second is the shifting. All right. All right. So in this case, if I have a factor of 2, we talked about this. If this number here is bigger than 1, which do I do? Expand or contract? I'm going to contract. Okay. So the first thing I do is I make for myself. I'm going to make for myself. All right. So if I thought of this guy as this is my original f of t. I'm looking at this guy, and what I'm first going to do is I'm going to make f of 2t. So I make this function g of t equal to f of 2t. Okay. And then I'm going to shift that guy. Okay. So if this is my function here, f of t, how do I apply that 2 here? We say we compact the signal, right? We compact it by a factor of 2. So I could go through this analysis here, right? So I could say at t equal to -2, that would be, what's the value of g of t? What's the value of f of t? Let's see if we can think about this though. If I took this thing and I were to compact it by a factor of 2, right? If I compact it by a factor of 2, what would that do? Where would it start and where would it end? -1. It would start at -1 and it would end at 1, right? This value here, this little minimum point at -1, where would that happen? -1/2. -1/2, right? And we could go through that very carefully, right? And in other words, I could plug in values of t, right? I could say that, let's see, that's sort of what I did here. So, no, I can't. Didn't delete that for myself. All right, so you know it's half though, so it's going to be flat until I get to -1, and then it's going to go down. Where's it going to be at t equal to 0? Yeah, so this point right here, does that point move? No. I'm just taking the whole thing and squeezing it in, right? So effectively, it's going to look like this. It's going to come up to 1. Then it's going to go over to 1, and then it's going to go down. It's going to go like that, right? I basically took all the points on the x-axis, the t-axis, and I compacted them. That means that the point right here at t equal to 0 didn't move, right? The point at t equal to 0 didn't move. If I think about f, so g of t is f of 2t. If I plug in t equal to 0, g of 0 and f of 0 are the same, right? So I'm moving everything around that point. All right, that's the first part of it. This guy here has been compacted by a factor of 2. So what we said is the first thing we do is I apply the scaling. The second thing I do is apply the shift. All right, so what's the shift that I apply? I've done the first step. I've done the scaling. According to this, what's the shift that I now apply? What's the shift? So I move it to the left by 1, right? So I move it to the left by 1. So the left would be, I did left. Left for me is not the left for you. Move this to the left by 1. That would be an advance, right? We call it an advance because it's happening earlier. Okay. All right. So this was the original f of t. This was the g of t that I just drew, right? This guy here is f of 2t. Okay. Now what I want to do is I want to take this g of t that I just drew and I want to shift it to the left by 1. So the picture that I drew right here, I said this guy's starting at -1, he's ending at 1. All right, so where is this? Where is the final function? This is y1 of t, which is equal to g of t plus 1, which is the signal I desired. Right? Not very exciting stuff. Right? Where do I start? So I'm going to take this and move it to the left by 1. So where do I start? As I go down the time axis, where do I start? -2, right? -2. This guy's going to start at -2. And whatever value I had at t equal to 1 is now at t equal to, t equal to, whatever value I had at t equal to 0 is now happening at t equal to -1. Right? Like that. All right. So the value, so the first step we did was to compact this. So that instead of going from -2 to 2, it went from -1 to 1. All right. That's what I have here. Now what I have to do is shift this result to the left by 1. So instead of starting at -1, it starts at -2. Instead of ending at 1, he ends at 0. That's all it kind of comes down to. All right. Now in the homework, you're going to have some stuff like this, but I will do it in terms of things like, what if I gave you, let's see if you guys remember. I'll do it here for a second. This function delta of t, I talked about it a week ago today. You weren't thinking about this a week ago today. Delta of t, how do I sketch that guy? So here's the time axis, right? What's delta of t look like? The function is defined, it's not defined at any value. What we said is his area is equal to 1, right? And he basically exists right here, t equal to 0, right? What he approximates is something that's useful to us. Like if I say, I have a unit step, what's the derivative at t equal to 0 where the step is going from 0 to infinity? Well, it's really big, right? Usually you guys say the derivative at a discontinuity is equal to undefined, right? Well, we need a definition for it in a formal mathematical context. So we use this notion of the delta function, right? This guy is something that is infinitely high and infinitesimally thin. All right. He's a person that's been stretched off to infinity, so he's perfectly skinny at that point, right? Basically what this guy is. It's saying that, but his area, it's a box with a width like this and a height real high. His area is 1, right? It's the definition that we give to it. All right. We talked about this last Tuesday. You can go back and take a look at it if you don't remember. It's a very simple thing, to be honest. I mean, it's complicated mathematically, but it's very simple to use. All right. The thing that we said previously is if I have a function like this, right? You go back and look at this in the notes and the lectures from last week. If I multiply the impulse by some function, then what this impulse has is something called a sifting property. And this guy pulls out a specific value of the function g. What value did he pull out? What value do you think he pulls out? He extracts one value. He sifts out one value of the function. What value of the function does he sift out? At what value of time? G of 0. Yep. Now, let's say I give to you, let's say I want to see delta of 3t plus 1. All right, delta of 3t plus 1. Now, although this is not formally mathematically correct, the easy thing for you to probably think of is, well, let's just think of delta of t is equal to 1 at t equal to 0, right? We'll just think of it that way. It's not really like that, but we'll think of it that way. All right. So where is delta of 3t plus 1? Well, I think of that as delta of 3 times what? T plus 1/3. Now, This guy's infinitesimally thin. Does that scaling mean anything for him? No, he makes skinnier. Right? That doesn't mean anything. Right? What about the 1/3? Shifts it. All right. Shifts it. In which direction does it shift it? To the left. So it's an advance, right? So it would move to negative 1/3, right? Is what this would be. Now, what if I told you I have some function that's got a couple of impulses? That guy can be compacted or expanded. All right. So if I told you I had, let's say this function, let's say I had the function x of t, which had two impulses, one at t equal to 0 and one at t equal to 1. And I said I wanted to do x of 3t plus 1. That could be compacted, couldn't it? Right. What would I do here? So big number, so a number bigger than 1. Was that a compacting or an expanding? It's a compacting. And it compacts it by a third. So what's going to happen to this guy at t equal to 1? Where's a third of that? He will move to 1/3. Then I'll move the function. All right. So you're going to see that in the homework. All right. Again, you're like, what are we? This is okay. You have imaginary numbers, and now we're doing things that are infinitely high, and that's the thing. This is a very useful concept in a formal sense because if I think about it, the way I think about this is like, let's say I'm closing a switch, right, and opening a switch. When I open a switch and that switch is controlling the current through an inductor, what happens? Well, V equals LdI dt. You've gotten that far in physics in circuits 1. Right? So when I open up a switch and I had a current going through it, there's an LdI dt. That current is going to go from some value to 0. Right? And that means that there is going to be a very large voltage that is created. In theory, if I can open that switch in 0 time, that voltage will be infinite. And that is why you see a spark when you pull the hair dryer. Right? Because it tried to create an infinite voltage. Or at least a voltage that was really, really big until the air said, we can't deal with that, and light thing. All right. The same sort of thing happens if you take a capacitor and you put a screwdriver across the terminals. Right? If I put a screwdriver across the terminals, you basically said I equals C dV dt, and you tried to make the voltage on the capacitor go from some value to 0 real fast. That caused a spark. Right? That was basically the current, the capacitor trying to become infinite. Right? So it is a useful concept for us in a lot of ways. Right, but I don't want to lose too much time on that. All right. So we talked about last week. I went through both on Tuesday and on Thursday this notion of I can represent a cosine wave 4 different ways. All right. You weren't thinking about that because you were thinking about your project. You were thinking about the exam. All right. Now it's time to think about this in your homework. This is problem 2, 3, and 4 in your homework. All right. Is to think through this. All right. So basically, we got 4 different ways to do it. The top way is the way we normally think about it in the context of just regular old, like if I have a circuit, right? We say with a circuit, and if I have an AC waveform, a cosine waveform, I can change the amplitude, I can change the phase. I can shift it left or right, make it bigger or smaller. That's what you guys saw in your differential equation stuff. You had at least 2 problems that covered that on the exam yesterday, right? I can think of that guy as also a sum of a cosine and a sine. Right? I can also think of it as 2 vectors rotating in the complex plane. Which of the vectors rotates in the clockwise and which one's the counterclockwise? Which one's clockwise? Which one's counterclockwise? Not you. Not you. Not you.
Positive J is the clockwise.
Positive J is counterclockwise, right? Because counterclockwise is the positive. So it's weird. It's the positive direction is the counterclockwise, right? And then this one is the clockwise, right? This guy here, we say this thing is also the real part of a rotating vector, a single rotating vector, okay? And then there's relationships between all these different coefficients that I've written out here, right? Which we'll be using shortly. Now, last time, I also went through this notion of what is a Fourier series. The basic idea was I said, if I have a periodic waveform, any periodic waveform, what does it mean for a waveform to be periodic? It repeats over a certain period of time, right? Our definition is if I have x of t, it's equal to x of t plus capital T. Right? This guy repeats after some time, capital T. So what I did was I said, okay, well, so the square wave that I have here, which is in this case got a period of 1, right? He goes from a time t equal to 0, he goes up to 2, and then a time t equal to 0.5, he goes down to 0. At t equal to 1, if I kept plotting him, he would go up again. He would just keep repeating, right? So what I did here is I kept adding in waveforms, sine waves that had harmonically related frequencies. What did I mean when I said harmonically related frequencies? So first of all, I said this guy, I forget how I came up with that amplitude, right? We're going to talk Thursday about how I get the amplitude. But I know I plotted something that had amplitude 4 over pi, right? I didn't pull that on my ass. There's a way to show that, right? 4 over pi times sine 2 pi over t. Where'd the 2 pi frequency come from? Why did I make a frequency of 2 pi for this? Yeah, so the frequency here is omega, right? Which is 2 pi over the period. What's the period? 1, right? That's why the frequency is 2 pi. I called this the fundamental frequency. It's the base frequency that this square wave has. All right. And then what did I add to this? Well, I said sine kind of fits in there nicely, right? But it's not, it's kind of got the same timing, or it has the exact same timing as the square wave. It kind of fits in there. Let's say I wanted to make them fit a little bit tighter to that square wave. What would I add to that sine wave to make it fit a little tighter to that square wave? What was the next thing I added to it? When I say fit it tighter, in other words, I kind of want to fit it in. So I've got it fitting horizontally. I want it to fit vertically. What should I do to get it to fit vertically into the square wave? Does it look like I should shift it up a little bit, right? I shifted it up by 1, and it looked like that. So now see this guy's fitting a little bit better. And what I said is I shifted it up by the average of that square wave. And the way I computed the average was I basically summed up all the points in this blue function over a period and divided by the period. That's not a sum. It's an integral. Integral is a sum over a period, right? For a continuous function, that's the sum over the period. Yeah.
Is that the integral of the square wave or the sine wave?
So yeah, good question. Let's just to be clear, the x of t that I'm talking about is the square wave. Okay. So sine by definition has a 0 average. It goes from -1 to 1, bounces around that, right? The square wave here, which starts at 2, goes to 0, he has an average of 1. Okay. I didn't have to do any calculus to either do that either, right? So this calculus here, right? Some of you will sit down and do that calculus. You don't have to, right? Because this is a rectangle. It's just the area of a rectangle, right? And it's pretty easy to do. All right, we'll see some of that later. All right. That sine wave now fits into that square wave. What do I add to that thing to get the summation to look even closer to the square wave? Right? So last Thursday, I kept adding stuff to that thing to get it to fit closer to the square wave. Well, I said what I did was I added harmonically related sine waves. What does it mean for sine waves to be harmonically related? What was the key thing? Same base frequency, but the frequencies are multiples of each other, integer multiples of each other, right? So if this guy has a frequency of 2 pi, the third harmonic would have a frequency of 3 times 2 pi. And the second harmonic would be 2 times 2 pi. And the fourth harmonic would be 4 times 2 pi. And the fifth harmonic would be 5 times 2 pi, right? So what I did was I said, all right, let me add to this guy a special amount of third harmonic. Doing that led to this picture. So he's, getting a little bit closer now. The combination of these things. Okay, so just to be clear, this is that reddish waveform. Okay. That summation that I've plotted there looks a little bit closer than this does. When I say closer, what I mean is that like the sine wave, if I look at where the sine wave is, he's getting closer to the square wave, right? So as I go from this picture to this picture, they're getting closer to each other. If I add in a fifth harmonic, they're even closer to each other. And if I go all the way up to the 99th harmonic, this is what I show here, they're yet closer, except they have these ears that are developing, right? All right, and those ears are always going to develop unless I conclude an infinite number of those harmonics. Okay? It's a basic concept of a Fourier series. All right, and it's useful for a lot of reasons. The most important one is those of you that are in circuits 2 know that if I only care about the steady state, and we know this too, like from just differential equations. If I said I don't care about the transient response of the differential equation, I only care about the steady state response, then I can use phasors. In circuits 2, if you're in that class, you don't even bother writing a differential equation. You just use the fact in circuits 2, you're saying, well, anytime I have a d by dt, that's the same as multiplying by j omega. And you called that impedance. Because if I make that understanding, so I've been mathematically formal in writing differential equations, right? Because we kind of have to in this class. In circuits 2, you use the fact that every time I have a derivative, you just replace it with j omega when I'm talking about steady state, right? And so what's useful about this is if you had to solve for a circuit that had a square wave going into it, you'd have to solve the differential equation by hand to figure out what the response is going to be to figure out the steady state stuff, and it's obnoxious. But if I use this approach, I can use impedance analysis at each of those individual frequencies in the Fourier series. That turns out to be a much simpler approach in general. None of you guys would be electrical engineers if this didn't happen, right? Because you'd just be solving differential equations all day long. Right? But because we can use this higher powered math, we can make a lot of simplifications to the math that we actually do. All right. All right. So that's why we worry about this stuff. All right. So a couple of key definitions that we made last time. We talk about the fundamental frequency. All right. The fundamental frequency, we say, okay, so the smallest frequency in the waveform or the largest period of the waveform. Okay. The harmonic number n, we talk about that, right? And then we talk about the DC or average term of this thing. We're doing there. All right. Remember the DC or average term. So what frequency is the DC term? Zero. So when n equals 0, all right? So n, this harmonic number, is what I multiply the fundamental by, right? And so what we said is that we represent this waveform, our general periodic waveform can be represented as one and actually as all three of these summations. So these are series, right? You learned Taylor series and things before, right? If I give you, let's say, an cosine n omega naught t, and I do that from n equal 0. Sorry, let's do it from n equal 1 to 3. What would I write here? Just to understand that. If I expanded that summation, so I go from n equal 1 to 3, how would I expand that summation? Be 3 terms, right? What would the 3 terms be? What would the first term be? Well, I plug in n equal to 1, which means I would write a1 times cosine what? Omega naught t. And we'll know what a1 is, right? That's what we solved for, right? And I would add to that what? A2 times cosine of what? 2 omega naught t. And then I'd add to that A3 cosine 3 omega naught t. And usually in our Fourier analysis, what we do is we're figuring out what is A1, what is A2, what is A3. And usually what we do is we figure them out in this series, because the calculus is a heck of a lot easier in that series. And then once I know them in this series, I can relate them to the others. Okay. All right. So last time we started with this. So I gave you this signal S of t. We actually went through the first two parts of this, parts A and B. And then I stopped at this last part. All right. So we're going to pick up with this last part again, but I want to review here real quick. So 10 plus 50 cosine 2 pi 1000 t plus 2 pi 1750 t plus 2 sine 2 pi 1500 t. So looking at that, that is a periodic waveform, right? If I plotted it, looks like this. All right. So what I see here is this guy does repeat, right? So I plotted it, and I see that basically at t equal to -1 times 10 to the minus 3. So at t equal to minus 0.001 seconds, that guy has a peak. And then at 3 milliseconds, he had a peak. So his period goes from -1 to 3 milliseconds, which means the period is 4 milliseconds, right? We did this last time, but so the way I got that was I said, well, 3 milliseconds minus -1 milliseconds. That's how long it took for that to repeat. So 4 milliseconds, right? Which, if I calculate a frequency in hertz, that would be 250 hertz. Okay. So this guy here, this is a plot of S of t, that signal. Okay. Now, the other way to do this is, and we don't usually focus on this a lot. Usually it's obvious. So usually you look at the graph it's a square wave, and I can see the square wave repeating at 1 gigahertz or whatever. Usually I can see that. In this case, looking at this guy, you can also use this thing called the greatest common divisor, which you learned at some point. All right. I don't know what grade, but you probably have forgotten it. The GCD function you can use in MATLAB. Thing is, GCD function only works with two numbers. So if you look at the way I did this, I've got 3 terms to include. So just the frequencies that I'm looking at here in hertz. What's this guy? So 2 pi 1000 t. What's the frequency of that in hertz? 1000. Right? 1000. 1000 hertz is the same as 1 kilohertz. Right? Kilohertz sounds like a wrestling move, right? So a kilohertz, right? And a megahertz, not a megahertz. That definitely sounds like a wrestling move, right? If I think about this, so 2 pi 1000 t, 2 pi 1750 t, 2 pi 1500 t. The fundamental frequency we found was 250. So the question we have that we sort of worked through last time is, what harmonics are here? Right? And the way I do this is I say, okay, well, let's go through for n and then nf naught. Let's figure out whether we have them or not. Okay. Now, looking at this, I've got some cosines, I got some sines. Which form of the series do I have here? Do I have this one? No. Do I have this one? No. Why don't I have this one? I got cosines. Well, because this guy's got cosines plus some angles added in. So what I have is a bunch of sines and cosines. I got the top form, the sine cosine version of the series. All right. I can make an equivalent version of this one and an equivalent version of that one. But what I was given was something in the form up top. Okay. All right. So help me out here. I want to figure out what frequencies I have, what harmonics I have. So I'm going to plug in for n equal to 0. 0 times f naught here is 250. So what frequency is that? Well, that's 0 hertz. What did I name 0 hertz? What frequency do I, or what term do I give to something that has 0 hertz? It's a constant, right? The number 1 is always constant. That's a DC signal. Constant signal is DC. All right, this guy is the DC term. Do I have a DC term in this? A constant? I do, right? The number 10. All right, so I do have one of those. All right, for n equal to 1, n times 250 is 250. Do I have a 250 hertz term in here? All right, this is the signal, S of t here. Does that have a 250 hertz term? No, it doesn't. All right, how about a second harmonic term? Second harmonic would be 2 times 250, which is what? 500, right? Do I have a 500 hertz term here? This one's 1,000. This one's 1,750. This one's 1,500. So do I have a 500? No. Third harmonic, what's that? 3 times 250. Do I have a 3 times 250? No. 4. What's fourth harmonic? 1,000. Do I have one of those? Yes. All right, so I got a DC term and I got a fourth harmonic term. All right, now I guess I got some more apparently here. So N and NF naught. All right, so for N equal 5, 6, 7. So 5 times 250. What's 5 times 250? 1250. All right. Do I have a 1250 term? No. All right. Sixth harmonic would be 6 times 250. 6 times 250 would be 1,500. Do I have a 1,500 hertz term? Yes. All right. All right. 7 times 250 would be 1,750. What's that? Do I have one of those? Yes. Now, in the problem here, and my problems in the homework kind of like this too, I say determine capital ND, which is the number of the highest harmonic frequency. So if a signal has 10 harmonic frequencies, then ND equals 10. So in this case, I would say ND equals what? 7. All right, this could be useful to me later. Okay, all right. So looking at this, what I then did is I just sort of pattern matched, right, to this whole thing. And I said we went through this last time. I said for n equal to 0, I have a DC term. So for n equals 0, the DC term is 10. So what I said was a sub 0 was equal to 20. Wait, that seems weird. Why did I say it was equal to 20? Well, because the way they define it, I didn't choose it. That's just the way it's defined, right? Is that the DC term is equal to A0 divided by 2. There's a reason why. All right. I'm not going to talk about it because it'll just confuse you more. Okay. All right. Now, what I would do is I look at this and I say, all right, I don't have a fundamental term. So those terms don't exist in the series. So so A1 and B1 are equal to 0. And I think of those as like knobs, right? I'm saying I don't need any amount of a cosine 250 with a 250 frequency or a sine of the 250 frequency. So I'm basically multiplying them by 0 to make them go away. All right. When I say a knob, I don't know, maybe I'm thinking of this the way that I think of electronics, right? So if I have you think about the volume knob, right? When you take the volume knob and you turn it all the way to off, right? You're basically multiplying a signal by 0. Right? That's what's happening, right? That's why I use that terminology. All right. I don't have a 500. Don't have a 750. We showed that the first term we have is a fourth harmonic. All right. If I look at the fourth harmonic here, all right, the fourth harmonic is this guy. All right. It's a cosine term. Because it's a cosine term, I said that A4 is 50. Why don't I have a B4 term? Why do I say B4 is equal to 0? with this series here, why do I say B4 is 0? All the B sub n values are the coefficients of the what? Sine. I don't have a sine for times 250t, right? I don't have that, right? So I only have the A. And if anything at 1250, there's nothing in that thing that has a 1250 hertz. There is a 1500 and there is a 1750. But I said the A values were 0. Why did I say the A values were 0? If this is our series here, why did I say the A values were 0 at 1750 and 1500? Because those are sine terms. There's no cosines there, right? So what I did was I said at 1500, the amplitude was 2. That's what this is. At 1750, the amplitude was 20. That's what this is. All right. So what I did is I sort of just pattern matched to this. So when you do your homework, I'm going to give you waveforms that have, different, that have different forms like this. And you'll have to figure out, okay, well, which terms do I have? And what are the amplitudes of the different terms in the series? All right. Now, the question I have here, what have I done? So what I've done here is I have written out a table that includes, if I want to go into the other forms of the series. So basically, we had this thing here. We said that I have an cosine n omega naught t plus bn sine n omega naught t. And there's another form of this, which is C0 over 2 plus there's an equivalent form of the series that exists like that. So what did I do here? Basically, I wrote a piece of code to do the conversion for me. All right. Now, how did I do that? So let's just, I got some stuff. I got a square root. I got an angle. The way I did that, the way I recommend you thinking about it, is I've got these formulas here, the notes now multiple times, right? I figured out, I derived before relationships between all of these different coefficients. And what I found is if I have a cosine sine form of a series, I can convert to the shifted cosine using the coefficients A and B, and then using these two formulas right here to figure out how those A and B values relate to the angle and how they relate to the amplitude. Okay. So what I did, all right, so let's see. What I did here is I said that at the frequency, at the nth harmonic, I said C sub n is the square root of an squared plus bn squared. And the angle phi n is equal to the angle of an minus j bn. Like that. And what did I do? I put the values an and bn into a set of vectors. Now, the vectors that I made there, those row vectors or column vectors? The an and bn, is this a row vector or a column vector I made? These are row vectors, right? So what did I do here? I said Cn equals square root of that. Now, what is that? Why did I do an dot squared, bn dot squared? What did I do here? I took every element in an and squared it. I took every element in bn and squared it. And then I took the square root of the sum of those two things. Now, if you don't like that, because it's like, all right, you're doing too much at once and you're doing dots, and I could do a for loop, right? And I could take out every value of an and bn together, right? And create the value of cn separately. You could do that, right? But I operated on the entire vector. You can do that. Okay. You do it either way. And then here I made the phi sub n values by implementing this. I took the angle of the vector an minus j times bn. And then I multiply by 180 over pi because I like degrees. Okay. So when I went through this, I found that, all right, these are the amplitudes that I got. Here's the angles I got. Okay. So these two guys have angles of minus 90 degrees. Okay. All right. So here then is my total code that I wrote. So what I did was I've got this, I have the GCD thing up there. That was helping me to figure out the fundamental frequency. And I said, here's how I did my A's, B's, and C's. Right? So you guys can look at that later when you're working on your code, because you'll probably want to do something similar. Now the question is, how do I get, and this just, how do I get between the alpha values? All right. So the alpha value. So let's take, so what we did before, let me jump up there to this guy, right, which is the sixth harmonic. All right. For the sixth harmonic, what we found was the sixth harmonic was 2 sine of 6 times the fundamental frequency. Okay. So what I can do for this thing, so let's do this. Let me write this out a little bit more carefully here. All right. So this is my sixth harmonic. So 2 sine 2 pi 1500t is the same as 2 cosine 2 pi 1500t minus 90 degrees. That's the shifted cosine version of this thing. Or it's 2 rotating vectors with a magnitude of 1 and an angle of negative 90 degrees, e to the j 2 pi 1500t plus angle 1, magnitude 1, angle 90, e to the negative j 2 pi 1500t. Right? 3 equivalent ways of looking at this. Now, what did I do here? So this says 2 over 2 e to the negative j 90. Why did I write it 1 angle negative 90? Because you guys like that better, I think. Right? If I say 1 e to the negative j 90 degrees, that's the complex exponential form of the polar number 1 angle negative 90. Right? I can totally do that. Right? Those two things are equivalent. Right? So I'm looking at this. In this form of the series, this is one form of the series. This is one form of the series. This summation of the 2 rotating vectors is another form of the series. All right. And what I called this, looking back at the terminology that I've got here, right? This guy has, I call these coefficients alphas. Okay. Now, one thing I want to see here, right? If I look at this form and this form, the summation starts at n equal to 1. For this one, it starts at negative infinity. Why does this guy, effectively, he looks like he has twice as many entries. Why? Yeah, to get the frequency omega, right, I have to have something. So to get a cosine with a frequency of omega, I have to have a negative rotating vector and a positive rotating vector. So I have a negative j omega naught t and a positive j omega naught t. So there's going to be 2 vectors that go with that. The good thing is the alpha so alpha 1 and alpha minus 1, we said, are always conjugates of each other. So if I go back to these relationships, right, alpha 1, alpha minus 1 are always conjugates of each other, right? Alpha 1, let's see, alpha minus 1 is always the conjugate of alpha 1. So their magnitudes are the same. Their angles are opposite. Okay. So how many terms? So let's just think about this. In this form, in the first 2 forms of the series, let's go to this one. The first 2 forms of the series, I had 8 terms that I was using, right? The 7 harmonics plus the DC term. How many am I going to have when I go to the complex formulas? Where do I have to start? So to piece this guy together, right? I said I needed essentially 7 harmonics plus a DC term. If I look at any one of these frequencies, so the frequency, I got a cosine or a sine of 1750 hertz. How many complex exponentials does it take to make that sine? 2, right? One at 1750 and one at negative 1750. So then how many terms am I going to have in the complex formula series? 15, right? 15. So 7 times 2 plus the DC term. I don't have a DC, I only need 1 term to make it. And that, if you think about it hard, is why there's the over 2 in the 2 forms of the series, right? Let me not say too much about that. Okay. If I look at this now, here's what I have when I do the complex form of the series. Okay. When I do the complex form of the series, I start at -7 and I go to 7. All right. So what have I done here? The first column says the harmonic number. The second column says the frequency. And then the rest of the columns have the coefficients in the series. These are the A and B coefficients. This would be for the sine cosine version. This would be for the shifted cosine version. These are the alpha values, right, for the Euler complex exponential form. Now, why did I say all these here? I wrote NA. Why did I write NA? So remember, these 2 columns are the sine cosine. This is the shifted cosine. How come I said those were NA? Because they're not part of the series. I don't need them, right? Because the series for those ones, right? For the sine cosine version starts at n equal 1. The shifted cosine starts at n equal 1, right? So I didn't need those terms, right? So I didn't need those terms. And so it's really easy to figure out the alpha values because what we said is that alpha n, his magnitude, is always Cn over 2, all right? And phi n is the angle of alpha n. All right, maybe I should write it the other way. The angle of alpha n is equal to phi n. So if I look at this here real quick, let's see. So for the 4th harmonic, right? I say he's got an angle of 0. Let's go to something where there is an angle, right? So for the 6th harmonic, I said that C sub n was 2. So that meant that the magnitude of alpha was 1, right? That's this relationship, Cn over 2. And I said that the angle was whatever that angle is, -90. Now, because alpha, so this guy I would call here, just to be clear, these 2 values make up what I would call alpha 6, which is apparently 1 angle -90. Alpha -6 is always the conjugate of alpha 6. So if I look at -6 all the way up at the top, the magnitude is the same. What do you notice about the angle? So here it is, right? What do you notice about this angle? It's 90, right? It's the opposite of the angle of the other one. It's the conjugate operation. All right, so, all right, real quick, I want to take a look at what I did here. So I got a for loop. So what I did was I was trying to make a piece of code that would figure out for me what the coefficients were. Now, in your homework, I ask you basically to give me a vector that has an, bn, cn, phi n, alpha n, right? You could make them by hand, and you might want to. Like, in other words, you could do what I just did with an. You could write, well, the first entry is this, the second entry is this, the third entry is this, the fourth entry is this. Or what I did here, which is a little bit fancier, right, is I basically wrote some code to do it. You can do that if you can. right? You don't have to, all right? But you should try, right? Now, what I'll do on Thursday is once I had these coefficients, if I wanted to, I could use those coefficients and I could make a plot of the series, all right? The important thing for you guys for right now is that you can figure out how to figure out what those alpha values are. This stuff starts on problem 2 of the homework. I would recommend that you try to start problem 2 before you come to class on Thursday. All right, it'll help you. All right.